Hello everybody and welcome to section 1.2 of the Art of Electronics, Voltage, Current and Resistance. This is the first real chapter of this book and it is jam-packed with 7 fundamental topics: voltage and current, resistors, voltage dividers, voltage sources and current sources, Thevenin equivalent circuit, small signal resistance, and an example of a circuit at the end to bring all this theory together. So, what is voltage and current? So voltage is the amount of energy it takes to move a coulomb of charge from point A to point B. So it is a loss or a gain of potential energy. So what do I mean by that? Well, imagine this scenario here where we've got a 5-volt battery. There are chemicals inside the battery that are trying to separate the charges. And for every 1 coulomb of charge that separates, it takes 5 joules of energy to do so. Is this energy just used up? Is it expired? No. Energy can't be created or destroyed, so instead it's stored as potential energy. This imbalance in charges means that the charges from one side desperately want to get to the other side. So, if we make a path for them to travel through, the charges from the positive side will immediately rush to the negative side. But along the way, these charges must lose the potential energy that they have. So for every coulomb of charge that travels through this path, they must lose 5 joules of energy. This energy is usually lost through heat in a conductor, but if we connect our own load to this circuit, then we can use this 5 joules of energy for something else. And that's basically it. Voltage is just a difference in potential energy. And for this reason, some people call voltage a potential difference, because it's a difference in potential energy. Sometimes it's also known as EMF or electromotive force, and this is because it is this imbalance of charges and this imbalance of potential energy that causes electricity to move in the first place. Now, voltage is of course measured in volts, and it is often represented by the letter V, and very rarely it can also be represented by the letter E if we're talking about EMF, and voltage is equal to joules per coulomb. So how many joules of energy it takes a coulomb of charge to get from one point to another. When speaking about voltage, we always talk about the voltage across something or the voltage between 2 points. We never say that voltage goes through something because that's just not how it works. Sometimes you might hear about people talking about voltage in one point of a circuit, and this is just the voltage across that point and a 0 volt reference, which is usually the negative terminal of the power source or something else that we call ground. So ground is our 0 volt reference. Now we move on to current. Current is simply the rate of flow of charge, or how fast charge is moving through a conductor. Now in maths, we often represent current with an I. The reason why we don't use C for current is because it's already used for capacitance. And the unit of measurement that we use for current is amps. Now, 1 amp is equal to 1 coulomb of charge per second. Now that you know what voltage and current is, let's look at a few laws. So the first law that I want to talk about is called Kirchhoff's current law, and it's a really simple law. It basically says that at any point in a circuit, the current going into that point, so I in, is equal to the current coming out of that point, I out. So if you have a circuit diagram like this one, any point where there are more than 2 paths connected, so here you got 1, 2, 3 paths connected, is what we call a node. And if we take this node for example, it has 2 currents out, so I guess we can rename these. You've got current 1 coming in, current 2 coming out, and current 3 also coming out. Current 2 plus current 3 is equal to current 1, because current 1 is the current coming in and current 2 and 3 are the currents coming out, and they have to be equal to each other. So Kirchhoff's current law is current in equals current out at any point in a circuit. Now for law 2, take this circuit diagram as an example. If you have a 0 volt reference, then at any point in the circuit there can only be one value for voltage. So say at point A we have 5 volts, and at point B we have 0 volts. Then that means that any path from path A to path B must lose 5 volts. So there will be a voltage drop of 5 volts across here, a voltage drop of 5 volts across here. If you had 2 components in this bottom path, then across both of them combined, there would be a voltage drop of 5 volts. And that is because the potential difference is always going to be the same here and here, no matter which path you take. Now, what Kirchhoff's voltage law states is that for any loop, if you go around clockwise and add up the voltages being lost or gained, it will always equal to 0 volts. So let's look at this as an example. So if we start from here and go around, right, 5 volts is lost across here. And if we go back around here, we know that in this direction, 5 volts are lost, but because we're traveling in this direction, there's actually a voltage increase, right? Going the other way, we're going from 0 to 5 volts, so there's an increase in voltage that way, which means we have negative 5 volts plus 5 volts. That is equal to 0 volts. So that's Kirchhoff's voltage law. The sum of voltage drop or gain in a loop must be 0. And last but not least, we have the power law. Now, what is power? Power is very easy to mistake for energy. But say, for example, you have an emergency exit sign and it's running off a really, really big battery. This battery might have kilowatts of energy. But this exit sign might only use a very, very, very small amount of energy at any time. Would you call this exit sign powerful? No, it is a low power device because it uses very little energy at any time. Likewise, you might have a very expensive gaming laptop, and inside of this gaming laptop, there might be only a very small battery. So it might not have much energy stored inside of it. But the energy it stores inside it, it uses really, really quickly. And you might even call this device power hungry. So you see, power is not simply equal to energy, but it's equal to the amount of energy a device uses over time. So if you take voltage, where voltage is the number of joules that a single coulomb of charge uses going from point A to point B, and you take current, which is equal to the number of coulombs passing through any point per second, and you multiply these two units, joules per coulombs and coulombs per second, then the coulombs cancel out and you're left with joules per second, or how much energy is being used over time. Which brings us back to our power law. The power used or lost by any device is equal to the voltage across it multiplied by the current going through it. And those are the 3 laws that you need to know about voltage and current.